Hi, in this video we're going to clean up a loose end from the April 1st video where we talked about finding e to the ta for square matrices when A was diagonalizable. So in these notes I'll talk about what to do when A is not diagonalizable, and this relates to a couple 2x2 matrices in your homework that's due for this week, and to other problems in that section which I did not assign. Okay, so as a warm-up exercise, use the power series definition for e to the t times a matrix to compute e to the tn for this matrix n. And I shall do it. So we know that e to the ta is just given by the power series as n goes from 0 to infinity of 1 over n factorial t to the n a to the n. So for this matrix capital N, e to the t capital N is the identity plus t times 2, 1 minus 4 minus 2. And now the next term would be t squared over 2 factorial 2, 1 minus 4 minus 2 squared, and so on. So let's just start computing powers and see if we can find a pattern. So n squared is 2, 1 minus 4 minus 2 times 2, 1 minus 4 minus 2. Let's see, the first entry is 4 minus 4 is 0. The second entry is 2 minus 2 is 0. This is interesting. For the 2, 1 entry, I get minus 8 plus 8, which is 0. And for the 2, 2 entry, I get minus 4 plus 4, which is 0. Well, since n squared is 0, that means that any higher power also equals 0, because it'll be n squared times a positive power of n, which will be 0 times a matrix, which is 0. So e to the t times n, so that's the matrix 2, 1 minus 4 minus 2, is just the first two terms. It's the identity plus t times 2, 1 minus 4 minus 2. And I can write that by just computing which each entry is. And so in the 1, 1 entry, I get a 1 plus a 2t. In the 1, 2 entry, I get a 0 plus t. In the 2, 1 entry, I get a 0 minus 4t. And in the 2 entry, I get a 1 minus 2t. Well, that's got to be just about the easiest matrix exponential we've computed yet. Okay, well, not every non-diagonalizable matrix, and this one actually is non-diagonalizable, has that easy of a matrix exponential, but it's related. So a matrix N is called nilpotent. It has no power if actually some power of the matrix is the 0 matrix. And if the dimensions are little n, then, and if the matrix is nilpotent, then it'll always turn out that by the time you take the matrix to the nth power, you get the 0 matrix. And sometimes a lower power will already give you the 0 matrix. Okay, and as we saw in the warm-up exercise, if a matrix is nilpotent, then the series for e to the tn truncates fairly quickly, because fairly quickly the powers of the matrix n become 0. Okay, so in this example, I have created a matrix which is related to the warm-up matrix. So we'll see how in a second, a few lines down. So this is a matrix with interesting eigendata, and you might have seen this kind of eigendata back in your linear algebra course. So if I take the determinant of A minus lambda I get a lambda squared from the diagonal product. I get a 4 lambda also from the diagonal product, and then I get a plus 4 from the off diagonal. That's lambda plus 2 squared. But when I try to compute the -2 eigenspace, I get the homogeneous system 2, 1, minus 4, minus 2, and the eigenspace is only one-dimensional. It's the span, for example, of the vector 1, minus 2. And when we had a characteristic polynomial for a matrix where the power of the lambda minus lambda j term was bigger than the dimension of the eigenspace, then we called those matrices defective, and those were exactly the matrices which were not diagonalizable. Okay, so in this 2 by 2 case, what we're going to do is we're going to decompose A as a linear combination of the identity matrix, and the multiple we'll take is the eigenvalue. So we'll write A as -2 times the identity, and then we just have to add back on the matrix that gives us back A. So the n was 2 times the identity plus A, which is the second matrix here. Okay, so you can double check the arithmetic, but it's all right. Now, remember, when two matrices commute, say A and B, then e to the t times A plus B is e to the TA, e to the TB. And so multiples of the identity matrix commute with all square matrices. And so in this example, e to the TA is e to the minus 2ti, e to the tn, so I'm just writing down what we're using. And so e to the t times 0, 1, minus 4, minus 4 is e to the t times minus 2, 0, 0, minus 2 times e to the tn. And we know that for diagonal matrices, e to the t times the diagonal matrix is just the matrix of exponentials of the diagonal entries. e to the tn, I should have copied from the other page, is the matrix 1, 1 plus 2tt, and minus 4t, 1 minus 2t. And the first matrix is just e to the minus 2t times the identity, so I can just write that as the scalar, e to the minus 2t times 1 plus 2t, t minus 4t, 1 minus 2t. So that's the final answer. For e to the ta. Now, it may seem like this was just a lucky accident, but it's true that anytime you just have a 2 by 2 non-diagonalizable real entry matrix, then, and this part is easy to work out from linear algebra and what you knew about defective eigenspaces, then it will be true that the characteristic polynomial factors as lambda minus lambda 1 squared, but the lambda equals lambda 1 eigenspace is defective, it's only one-dimensional. And then it will always be true that if you just rewrite A as the eigenvalue times the identity matrix plus A minus lambda 1i, which that second matrix will be nilpotent, and e to the ta, and lambda 1i commutes with every square matrix of the same size. So e to the ta will always be e to the t times lambda 1i, which will turn out to be e times lambda 1t times the identity matrix times e to the tn. So for 2 by 2 matrices, that's how to deal with the non-diagonalizable case. Okay, so let's cross-check our work. So this first order system that we just considered actually came from a second order critically damped differential equation, and we can check that because if we look at x prime for solutions to the second order dE, that's x prime, x double prime, and x double prime is minus 4x minus 4x prime, and that is the matrix 0, 1, minus 4, minus 4 times x prime. So remember, one way that we talked about in the last lecture to compute e to the ta was to solve initial value problems, if A came from a second order differential equation, was to solve initial value problems where the initial data was either 1, 0, or 0, 1 for the second order dE, and then those were the columns of e to the ta. So we know that that the characteristic polynomial for the second order dE is, well, it's going to be the same as it was for the matrix, but here, let's just double check, r squared plus 4r plus 4, which is r plus 2 squared. And so the homogeneous solutions to this critically damped unforced dE were C1 e to the minus 2t plus C2t e to the minus 2t. Okay, so if x of 0 was going to be 1, and x prime of 0 was going to be 0, then x of t, so we'll need a 1 e to the minus 2t, and then that'll make x of 0 1, and then when I take x prime, I'll get a minus 2 from the exponential, and then plus a c2, so I want plus 2t e to the minus 2t, and x prime of t will therefore be, I can see a minus 2 e to the minus 2t, plus a 2 e to the minus 2t, minus a 4t e to the minus 2t. And when I'm looking at e to the at, x prime, because those are the x1, x2, for this initial value problem will be the first column. To get the second column, I'll solve the initial value problem where x of 0 is 0 and x prime of 0 is 1. So in that case, I don't want any pure exponentials. I'll want a multiple of t e to the minus 2t. And when I take the derivative of that and set t equals 0, I'll already get, well, I'll get 1, right? So that x of 0 is 0, so my constant in front is just going to be 1. And x prime of 0 will be 1, so x prime of t, I'll just take the derivative, will be e to the minus 2t minus 2t e to the minus 2t. And that will be the second column. Of e to the at. And of course I can factor an e to the minus 2t out of each term. Then I'm just left with 1 plus 2t, 1, minus 4, 1 minus 2t. And now let's scroll back to the previous page. 1 plus 2tt minus 4t, minus 4t, 1 minus 2t. Ta-da! Okay. Now, I just told you how to do the 2 by 2 non-diagonalizable case of computing e to the ta. And there's a theorem called the Jordan-Chevalley decomposition, which says for n by n matrices, if A is not diagonalizable, then you can still decompose A as B plus n, where B is diagonalizable, n is nilpotent, and n and B commute. And so therefore, we know that e to the ta will be e to the tb times e to the tn, and we now know how to compute e to the t times a nilpotent matrix. Those are the easiest in the world. And since B is diagonalizable, we know how to compute e to the tb, either using a fundamental matrix solution whose columns are of the form e to the lambda tv, or using the diagonalization identities, which are related to that. All right, so let me just say a few words about this Jordan-Chevalley theorem. It's one way to understand it is via a better known theorem, which is called the Jordan decomposition theorem, which says that every matrix A is similar to a matrix in Jordan-Canonical form, which is like the next best matrix you could have after a diagonal matrix. So that means there's some matrix P, so that P inverse A P is one of these almost diagonal matrices. And our text actually deals with non-diagonalizable matrices in section 5.5, and they show how to construct fundamental matrix solutions for the system. So remember, that's just a matrix whose columns are a basis for the solution space. And then, as we talked about last time, if you just take phi of t times phi of 0 inverse, you get e to the ta. So the text, in my opinion, doesn't really give you, it's there, but it doesn't sort of emphasize the big picture. And it's fairly technical, and so that's why we skipped it. So if you want to understand the big picture, I would recommend trying to learn about Jordan-Canonical form. And here's an example to just give you a flavor for how things go using the Jordan-Canonical form. So suppose we had a 3 by 3 matrix, but its characteristic polynomial was lambda minus 3 cubed, and the eigenspace was only one-dimensional instead of being three-dimensional. Then you can make a matrix P of what are called generalized eigenvectors, and they'll actually be a basis, in this example, for the null space, not of A minus 3i, but of A minus 3i cubed, which is a larger space, because if A minus 3i doesn't kill a vector, then maybe A minus 3i times A minus 3i times that vector is 0, and so on. And in this example, that would actually be, that null space is all of R3. Okay, and in this, the way Jordan blocks always look is that they're the eigenvalue times the identity matrix plus a matrix n, which is 0 except for its ones along what they call the super diagonal, so one above the diagonal. And in this example, n is the matrix which has zeros everywhere except it keeps the two ones. And when you compute n squared, the ones drift to the right, and you've just got a 1 left in the upper right-hand corner. And then when you compute n cubed, it's 0. Okay. And the identity matrix, or multiples of it, commute with any matrix. So if A was P, J, P inverse, then as we saw when we were doing power series and diagonalization, e to the TA when we just put in those power series for powers of A, everything will have a P on the left and a P inverse on the right, and in the higher powers, everything telescopes. So we have this identity, so that's what we did before. And then since J decomposes into the sum of two commuting matrices, we can replace e to the tj with e to the 3 times the identity times e to the 3t times the nilpotent. E to the 3t times the identity matrix is just e to the 3t times the identity matrix, like in the example. And so we get this final identity. All right, and you can check, because n cubed is 0, that the e to the 3t n in this example just has that pretty form, and then the final, or the semifinal, e to the 3t I times e to the 3tn has this form, and then finally, to get e to the ta, you'd have to multiply on the left by p, and on the right by p inverse. Okay, so that's just to give you a flavor of how you compute matrix exponentials for non-diagonalizable matrices. And so the upshot is that if A is not diagonalizable, well, if A is nilpotent, meaning if a finite power of it is 0, is the 0 matrix, then e to the ta is only a finite sum using the power series definition of e to the ta. So that's super easy. If A equals B plus N, where B is diagonalizable and N is nilpotent, and N and B commute, then e to the ta is just e to the tb, e to the tn, and we know how to compute each factor. Okay, so hopefully that gives you a feeling for what to do if your matrix is not diagonalizable.